Dear students, we begin our practices on mathematical analysis 1. So the first topic is method of mathematical induction. Let's give the definition of method mathematical induction. Mathematical induction is a common method of proving that each statement of an infinite sequence of mathematical statements is true. The principle of math induction contains proving of mathematical statements in 3 steps. So the first steps, let P and be a statement involving natural numbers. Then first one is prove that P1 is true for n equal to 1. So here it show mathematically it works for n is equal to 1. The next step, second step, it is assume that Pk is true for n is equal to k. Here there is no proof here. Truth of one statement implies truth of the next statement. And the third step, it is prove that pk plus 1 is true for n is equal to k plus 1. This statement builds from the step 2. And conclusion, by mathematical induction, the above statement is true for all natural numbers. Okay, let's consider the examples. The first exercise, use mathematical induction to prove that the sum of the first n odd positive integers is n squared. What does it mean? So it means 1 plus 3 plus 5 plus etc. to n minus 1 is equal to n squared. So the sum of the first n odd positive integers. Solution. Okay, first step, prove that P is 1 is true for n is equal to 1. We should prove it. Okay, so here what we have, 1 is equal to 1 squared. So does it equal? Yes, of course. So it is 1 is 1. It is obviously. So this is correct statement, the first one. Okay, in P1 it is true. And now second step, assume Pk is true for n is k. So we should rewrite our statement with k. 2k minus 1 is equal to k squared. So we just rewrite our statement with k because n is k. We should assume it. Now the main step, it is third one. So this is main step. Prove that pk plus 1 is true for n is k plus 1. So let's consider from step 2 what we have. We have this equality. Okay, now we should add the next term. So the next term will be 2k plus 1 minus 1, because instead of k we should put k plus 1. So we have k squared plus 2k plus 1 minus 1. So we added both sides of our equality this next term, this term, here and here. So here and here. So we want right hand side it's equal to k plus 1 squared. If we prove it, so we prove our statement. Okay, if we continue, what we have, k squared, if we open the brackets, so then after that we have k squared plus 2k plus 1. So what it gives us? It gives us k plus 1 squared. So we prove that right hand side is equal to k plus 1 squared. Again, we added next term to both sides of our equality, and we have in right hand side k plus 1 squared. So conclusion, by mathematical induction, the above statement is true for all natural numbers. Okay, now the next exercise. Use mathematical induction to prove for all positive integers n. Okay, what we have 1 squared plus 2 squared plus 3 squared and plus 3 plus n squared. So this sum of uh, the sum of squared one this and the right side we have n plus 1 2n plus 1 over 6. So again, first we should prove that p1 is true for n is 1. Okay, so what we have 1 squared, this is first term, so it means p1, and here we should put instead of n again 1. So 1 plus 1 2 multiplied by 1 plus 1 over 6. So what we have just 1 is equal to 1. So we proved the first statement, the first step. This is true. And now second step, assume pk is true for n is k. So we just rewrite our statement with k. Instead of n, we should put k. And then we will use this second step when we prove the third step. Okay, third step prove that for the next one, p k plus 1 is true for n is k plus 1. So here we have from second step this equality, and then again we should add the next term to both sides of our equality. So the next term will be k plus 1 squared, because this is sum of squared of numbers till k. So here we should add the next one, k plus 1 squared, and in the right side also k plus 1 squared. If we add the similar terms, it will not change. So this our statement will not change. Equality. Okay, so we want to right hand side to get instead of k each k plus 1. So it will be k plus 1, k plus 1 plus 1, and 2 multiplied by k plus 1 plus 1 over 6. So it gives us this one. If we prove that the right side of our equality equal to this expression, so we prove the statement is true. Okay, let's continue over our right hand side. So we have if we get common denominator, so factor out k plus 1 first. So we have this expression. If we continue, we get this one. So k plus 1 multiplied by 2k squared plus 7k plus 6 over 6. And if we continue, if we simplify this one, so factorize, we have k plus 1, k plus 2, and 2k plus 3 over 6. So we can write this expression with like this one. So k plus 1, instead of k plus 2, we can write k plus 1 plus 1, or instead of 2k plus 3, we can write 2 multiplied by k plus 1 and plus 1 over 6. So this is equal with this one. So we proved that for the next n, so k plus 1, this is true with using the second statement. So by mathematical induction, the above statement is true for all natural numbers. So to prove the statement, we should prove these three steps. Again, so first one is when n is 1. The next one is we assume that when n is equal to k, and in third step we will use this second assumption to prove for the next n. If we prove the for the next n, it means for all values of n we prove this statement. Exercise number 3. Use mathematical induction to prove that this statement is correct for all positive integers n. Solution. Okay, step 1. We first show that p1 is true. So it means instead of n, we should put 1. Right side, it is just 1 cubed, it is 1, and left side, sorry, and right side, it's equal to 1 squared multiplied by 1 plus 1 squared over 4. It's equal to 1. Hence, 1 equal to 1, and the first assumption is correct. Next step, we now assume that pk is true. So we should just write our statement by k. And the last step 3, prove that pk plus 1 is true for n is k plus 1 for the next n. So what we should do, again, we should add what? K plus 1 cubed to both sides, because we have cubed, 1 cubed, 2 cubed, 3 cubed, and n cubed. So we should add the next one. So it will be k plus 1 cubed. We use the second assumption. So here we add to both sides of our equality, k plus 1 cubed. And there is no change in our equality. They are again equal. So, but when we factor k plus 1 squared on the right side, here, what we have? K plus 1 squared multiplied by k squared over 4 plus k plus 1. So now what we have, and when we do this factorization, set the common denominator and group. So k plus 1 squared multiplied by k squared plus 4k plus 4 over 4. We get common denominator. And at the end we have k plus 1 squared multiplied by k plus 2 squared over 4. So we do simplifying and factorization of our right side. And after operations, we have this expression. And what it gives? It gives us when we put instead of k plus 1 here in second assumption. So we have what we have, k plus 1 squared, k plus 1 plus 1, k plus 2 squared, and over 4. It is, so here it's written, so we have started from the statement pk and shown that this one is true. So it's true for the statement pk plus 1. So we proved our statement. So we proved for the next n. Here, of course, n is natural number. Number 4, exercise number 4. By using mathematical induction, prove that the given equation is true for all positive integers. So here what we have, multiplication, 1 multiplied by 2, 3 multiplied by 4, 5 multiplied by 6, plus etc. 2 and minus 1, odd number multiplied by even number. So it's equal to this one. So we should prove it now. Solution. Step 1. From the statement of formula, when n is 1, left hand side, it is 1 multiplied by 2. It gives us 2. And the right hand side, it is when we put instead of n 1, 1 multiplied by 1 plus 1, 4 multiplied by minus 1 over 3, it's equal to 6 over 3. It's equal to 2. So it gives us that it's proved that P1 is true for the equation. So we proved for n is 1. Now we should prove for, firstly, we know, assume that pk is true. This is second step again. So just rewrite our equation with k, and the next step, third step, in the main step, we prove that pk plus 1 is true for n is k plus 1. So we should prove now with using the second assumption. We prove for the next n our statement. Okay, so left hand side, it's equal to this one, 2k, and we can add here instead of we can add here the next term. So it is this one, 2k plus 1 minus 1 multiplied by 2k plus 1. We add the next term, k plus 1 term, and it's equal to, from the second assumption, this part till this 2k, 1 till this 2k, it's equal from second step to this one. And now we add this expression, this term. Okay, so what do we have? After simplifying, we have such kind of expression. So it's equal to this one. And after simplifying again, factorization, we have this expression. And what it gives? It gives us k plus 1 multiplied by k plus 1 plus 1 and multiplied by 4k plus 1 minus 1. So this is showed it's true for k plus 1 term. Okay. So here we just multiply and we get this. After multiplying, we can take this k plus 1 out of the brackets, and we have this one inside of the brackets. So right hand side for p for it gives us right hand side for pk plus 1. Now it's proved that pk plus 1 is also true for the equation. So we proved our statement. Exercise number 5. By using mathematical induction, prove that the given equation is true for all positive integers. So here we consider this statement. So 2 plus 6 plus 10, and the general term, it's 4n minus 2. It's equal to 2n squared. Let prove this statement. Again, so we begin with first step. step 1 from the statement formula when n is 1, left hand side it's 2, it is first element. N is 1, it means the first element, first term, or and right hand side it is instead of n we put 1. 2 multiplied by 1 squared, it's just 2. So P1 is true, 2 equal to 2. Now step 2, now we assume that Pk is true, or thus we rewrite our statement with k here instead of n. And step 3, for Pk plus 1 we should prove it now. So left hand side it's equal to this one, 2 plus 6 plus 10 and 4k minus 2, and we should add this new term, last term, k plus 1. So it will be 4 instead of n, just put k plus 1 minus 2. So now after simplifying what we have this part. So this part we had, yes. When we changed n with k, this 2 plus 6 plus 10 until 4k minus 2, the sum of these expressions are equal to 2k squared. So you can change now this this expression with 2k squared, and we have 2k squared plus 4k plus 2, it's equal to k plus 1 squared, reducing short multiplication formula. Here we have 2 out of the brackets. Forgot this 2. Here we have just 2 take out of the brackets, and here 2k plus 1 squared, and it gives us right hand side for pk plus 1, 2k plus 1 squared. Now it's proved that the pk plus 1 is also true for the equation. So the given statement is true for all positive integers. So here we have 2, of course, 2k plus 1 squared, and then we have the same statement with this one. Exercise number 6. Prove that for any positive integer number n cubed plus 2n is divisible by 3. So how we prove it? Again, we have just let's take first step. First, we show that P1 is true. Let n is 1 and calculate n cubed plus 2n. So it is 1 plus 2, it is 3, and 3 is divisible by 3. Hence, P1 is true. So just we proved for n is 1. Okay, now step number 2. We now assume that pk is true, and so it means k cubed plus 2k is divisible by 3, or here divisible by 3. So it's equivalent to k cubed plus 2k is equal to 3m. However, it is divisible by 3, where m is any positive integer. So we can write this one like this expression. Okay, step number 3. Now we consider the algebraic expression k plus 1 cubed plus 2k plus 1. So here we should show instead of n, k plus 1 for the next n. Expand it and group like terms. We have this one, k cubed plus 3k squared plus 5k plus 3. And if we group it, so we have k cubed plus 2k and plus 3k cubed plus 3k plus 2. So we can write 5k like 2k plus 3k. And however, k cubed plus 2k from the second step, from the assumption, it's equal to 3m. So we can change k cubed plus 2k with 3m plus 3 multiply. We can take out of the bracket this 3 and we have 3 k cubed k squared plus k plus 1. So it's equal to 3 and we have common factor 3. So it will be 3 and in the bracket this one m plus k squared plus k plus 1. It doesn't matter in bracket what we have. This one is the main one. So this is 3 multiplied by this bracket. So by this expression. So it means it is divisible by 3. So we proved for k plus 1 it is also true. Exercise number 7. Prove that 3 the power of n it's greater than n squared. So for n is 1, n is 2, and use the mathematical induction to prove that this one for n a positive integer greater than 2. We should prove for any positive integer greater than 2. Okay, solution. Step 1. So we first show that P1 is true. Let n is 1 and calculate 3 the power of 1 and 1 squared. So 3 is greater than 1 and hence we have P1 is true. Okay, the second step. Firstly, we should show for n is 2 also, and here 9 and 4. 9 is greater than 4, hence P2 is also true. And now step 2. We now assume that pk is true, that it means 3 the power of k is greater than k squared. Now we should prove for any positive integer greater than 2. We showed for 1 and 2 firstly. Okay, and step 3, multiply both sides of the above inequality by 3, and we have, if we multiply to the same number both sides of our inequality, it doesn't change. So the left side is equal to 3k plus 1, the power of k plus 1, and the 4k greater than 2, we can write here k squared is greater than 2k, and hence we have k squared is greater than 1. We now combine the above inequalities by adding the left hand sides and the right hand sides of the two inequalities. We have 2k squared greater than 2k plus 1. We now add k squared to both sides of the above inequality to obtain the inequality 3k squared is greater than k squared plus 2k plus 1. So we just add the k squared to both sides of the above inequality here. Factor the right side. We can write 3 multiplied by k squared is greater than k plus 1 squared. So what it gives? If 3 multiplied by 3k greater than 3 multiplied by k squared and 3 multiplied by k squared greater than k plus 1 squared, then we have 3 multiplied by 3k is greater than k plus 1 squared. So we write the left side as 3k plus 1. Again, we have 3k plus 1 the power is greater than k plus 1 squared, which proves that k plus 1 is true. So what we did for this one, so again we here left side we write as 3k plus 1, and then for k is greater than 2, we can write these inequalities, and we add k squared both sides of this inequality, and we factor this one, and when we rewrite the left side, so we have this inequality, and it shows us uh, it shows us the statement is true for k plus 1. So we proved our statement, our inequality in this case. Thank you for attention.